Good evening, everyone. This is Drew Bartlett. I'm the Executive Director for the South Florida Water Management District, and thank you for joining us this evening for the C-43 West Basin Storage Reservoir Feasibility Study update. I see a lot of familiar names on the attendee list, and I like seeing your names. I wish I could see your faces. That we are in a sort of a new era right now. So this is the third meeting, and while we're not in person, we're all together under this webinar, and I really couldn't be more proud of district staff and everyone pulling together to make sure we stayed on schedule and had this meeting when we had scheduled it, even though we're not in person. This project and this feasibility study is critical to the future of the C-43 Reservoir project and the Caloosahatchee Estuary. And so the one thing that we have emphasized at the Water Management District in these difficult times is that we are going to stay committed to the mission and get the job done that the public expects us to do. That is why we continue to have this feasibility study meeting, and we're doing it with all the new technology that we're bringing to bear. So if there's any technology hiccups, please bear with us. I think it's important for us to get the information out to the public in a timely way so we can continue the progress on this feasibility study and put us in the best position to answer the questions and take the next steps on providing good quantity and quality water to the Caloosahatchee Estuary. I really want to also thank the work group for their dedication to this project. With your help, we have been able to stay on schedule, and today we've got the results of your hard work on pulling together, narrowing the options down to 10 so that we can present it to the public. So I know you're on the phone, and so I really appreciate your participation and strong engagement throughout this whole process. We have certainly set up this meeting to try to be as interactive as possible, given the limitations of not being in person. So hopefully everyone will get everything they need out of this workshop. If not, everyone knows that you can call anyone at the district working on this project and certainly engage and get answers. So at this time, I'd like to go ahead and turn it over to Georgia to go ahead and run the meeting. And thank you everyone for signing in this evening.
Thanks, Drew. Good evening, everyone, and welcome to the third public meeting on the C-43 West Basin Storage Reservoir project. My name is Georgia Vince, and I'm supporting the district on this important project, and we are excited to bring you this virtual public meeting via Zoom technology. We look forward to an interactive meeting with you, the participants, using this technology. First, I'd like to talk to you about the question sessions that we're going to be having. We'll have the opportunity for a few questions at the end of each section of the presentation, and you'll be able to raise your hand. And when you are called upon, please unmute your mic to ask your question. Some devices may show the raise your hand option a little differently. And we ask that you keep your questions pertinent to the topic that was just presented. If you are calling in on your phone only, you can press #9 to raise your hand and #6 to mute or unmute your phone. And if that's not easy enough for you to communicate with us, we also have a website, an email address that is available to provide feedback and input at any time. At the end of the presentation, we'll be utilizing another program called Menti to obtain input and feedback from Zoom participants. We'll have a second question and answer session at the end of the meeting where you can type in your questions regarding the information presented today. You'll have to access Menti from a separate internet browser or from your smartphone, and we'll provide the website address and code when we get to that portion of the presentation. I'd like to thank the working group members that have been supporting us on the study. They include several municipal entities within the region, and the following are our working group members. From the South Florida Water Management District, Kim Fekoski is our project manager. From the Florida Department of Environmental Protection, Ed Smith is the Director of Office and Water Policy and Ecosystem Restoration. Henry County, we have Shane Parker, the Public Works Director. Lee County, we have Roland Adelini, the Director of Natural Resources. From the City of Cape Coral, we have Maya Robert, the Environmental Resources Division Manager. From the City of Sanibel, we have James Evans, Director of Natural Resources. And from Lehigh Acres, we have Michael Cook, the Assistant District Manager. The consultant team leading the study efforts is JTEC, which is a joint venture between Jacobs Engineering and Tetra Tech. You'll be hearing from the consulting team today during the presentation, including Sean Waldeck, Jim Bays, and Chris Keller with Wetland Solutions. The purpose of today's meeting includes an overview of our study goals and objectives, an update on our information collection report and key findings, and to obtain your input for our study. And as I mentioned before, we'll be using another tool called Menti later in the presentation. Although this is our third meeting to discuss the project, this is our first evening meeting, and we would like to provide some background on the project for any new participants. So let's go back and take a look at the big picture. In January of 2019, Governor DeSantis signed an executive order to greater the protection of Florida's environment and water quality. It included efforts to reduce harmful algae blooms. Specific to today's topic, it included a directive to study additional water quality treatment opportunities for water leaving the C-43 West Basin storage reservoir. DEP is leading many efforts outlined in the executive order, including Harmful Algae Bloom Task Force, the Blue-Green Algae Task Force, the Caloosahatchee Basin Management Action Plan update adopted in January of this year, and agricultural BMP assessments with the Department of Agriculture and Consumer Services. DEP is also serving on the working group for this study and is managing the technology library, which is accessible on their website. You'll be hearing more about the technology library soon. The primary objective of this study is to identify opportunities to provide additional treatment and improve water quality leaving the C-43 reservoir. During the study, we will identify and evaluate treatment technologies that may be implemented with the reservoir project, with the ultimate goal being identifying 3 project alternatives. The study will evaluate pre-treatment opportunities prior to entering the reservoir, in-reservoir treatment, and post-reservoir treatment. We'll ensure the technology is cost-effective and technically feasible, and we will look at conventional and innovative treatment methods. We're considering biological, chemical, and physical water quality treatment technologies, and they must be scalable and available for long-term operation. They also must be compatible with the objectives of the C-43 West Basin Storage Reservoir project. The working group and consultant team have identified some constraints that we will need to keep in mind as the study moves forward. The identified alternatives cannot affect the congressionally approved C-43 reservoir project purposes, benefits, infrastructure, construction schedule, or operation. And we have not identified, project lands have not been identified specifically for this study. Here's our project schedule. The information collection summary report that we've been working on for the past few months will be available on the project website on April 3rd. We have our final public meeting on July 16th, and the final feasibility study with recommendations will be submitted in October to the Water Management District. So at this time, we will take questions, any questions that you have on the material that was presented so far. Again, if you go to your Zoom options, you should be able to raise your hand. And I will put that slide back up for you, and we'll take a few questions at this time.
Okay, Matthew, you are unmuted.
Yeah, hey, thanks for having this. I just have a quick question because I haven't attended these meetings. Could you talk about the status of the reservoir itself? Where it is in terms of the construction, if water is going in, if any water is going out right now? Because I'm a little bit lost in the conversation without that.
Okay, well, that's a good intro to the next section of our presentation. We'll be giving you an update on the storage reservoir itself and a little bit more about the workings of it.
Thank you.
Thank you. Henry, do we have any more hands raised?
That's it for now.
Okay. At this time, I would like to hand over the discussion to Sean Waldeck to discuss the important details about the C-43 reservoir.
Thanks, Georgia. I'm Sean Waldeck. I'm the site manager for the construction of the C-43 reservoir project. Just to give you a quick little overview of the project itself, it's a component of the Comprehensive Everglades Restoration Plan. It was funded by annual, or it is funded by annual state legislative appropriations and U.S. Army Corps of Engineers credit for eligible project costs. So this is a cost-shared project that was cooperated with the Corps of Engineers, and many of the design and construction components are consistent with their requirements. The basic project purpose is to capture excess basin runoff and Lake Okeechobee releases within the C-43 basin, or the Caloosahatchee River Basin, with the primary purpose to store water to improve the quantity, timing, and distribution of those discharges into the Caloosahatchee estuary to maintain proper salinity levels within the estuary. And another purpose is to maintain existing water supply for those legal users along the river. Next slide, please. So for those of you who may not know where the reservoir project is located, it's roughly halfway between the Ortona Lock to the east and the Franklin Lock to the west in the Caloosahatchee River, just on the west border of Hendry County, outside of LaBelle. And it's a 10,000 acre reservoir project, very, very large earthworks and dam project. And it's an above ground storage that will take water out of the Caloosahatchee River through the Townsend Canal. There's an existing water supply canal that serves the existing farmers in that area. And at certain times of the year, when the river and the estuary call for it, water that's stored in the reservoir will then be discharged back out of the reservoir, back into the Townsend, and then back into the river and through the lock at Franklin and into the estuary. A little more zoomed in picture of the reservoir itself. Again, it's 10,500 acres. It's divided into what we call two cells, and it's separated by a separator dam. They're of a roughly equal size. And again, the water is drawn in through the Townsend Canal into a very large pump station that lifts the water out of the Townsend Canal and places it into the reservoir. And then again, as the estuary calls for those water needs, water is then discharged out of each of the two cells along the perimeter canal that you can see bordering the northern portion of the reservoir, and then back into the Townsend and back out to the river. Next slide, please. So to recap, some of the major constraints are Lake Okeechobee operations schedule. as well as the Caloosahatchee estuary minimum flows and levels established at 457 cubic feet per second. That's the design discharge out of the reservoir back to the river. Repeating that it's operated to store that excess basin runoff and Lake Okeechobee releases. And the purpose of which is to maintain those salinity levels in the estuary past the Franklin Lock, which the Corps of Engineers calls S79. We'll fill it during the wet season on average and discharge it during the dry season on average. And those discharges and inflows will be based on what the flow conditions are at the S79 or the Franklin Lock facility. The inflow capacity of the pump station is 1,500 CFS. That's how much water we can fill into the reservoir. The size of the reservoir means that at 1,500 CFS, we'd be filling about 3 inches per day during the wet season. And in emergencies, we can discharge up to 2,500 CFS, although the standard normal outflows are to meet the MFLs at about 450 CFS. Next slide. And maybe just to answer Matthew's question, the reservoir construction started with, the contract was issued in June of last year, and the anticipated or the contract substantial completion date is December of 2023. Any other questions?
So yeah, if you have any questions for Sean, please raise your hand in the Zoom meeting and Henry will call on you when he's unmuted your mic.
Our first speaker will be Holly.
Holly, make sure you unmute your mic.
Hi, sorry about that. Will the planned toll road have any impact or influence on this project?
Can you repeat? Did you say toll or tow?
Yes, sir. Toll, T-O-L-L, the mid-state toll road.
I don't think so. I'm unaware of a toll road plan in the vicinity of the reservoir.
Okay, thank you.
This is Drew Bartlett. Yes, it will not. So it is the footprint of this reservoir has been designated as not a viable place to put it. So it will not.
Okay, thank you.
Mm-hmm.
Okay, our next speaker will be Chad Gills.
Hi, thank you. The 457 CFS, that's measured at Franklin Lock. I'm just double checking.
Yes.
And then with, it shows the above 2,500 for emergency discharge. Is what kind of situation would that be? Would that be like a potential flooding there within the...
Correct. So it's an above ground impoundment. So it's surrounded by a dam.
Mm-hmm.
And in the event that we identify a problem with the dam when the reservoir is full and we have flood conditions approaching, we can evacuate the reservoir pretty quickly so that we can protect the reservoir itself as well as everybody that lives and works around the reservoir.
Okay, thank you.
Our next speaker is Matthew Schwartz.
Okay, unmuted. I just had one more question about the construction. Thank you.
Sure.
How high are the finished walls of this above ground reservoir? And how high will the water level be when it's full?
Good question. So the dam embankments or the walls will be approximately 35 feet above the existing ground surface. So you might if you're driving on State Road 80, you might already see some of the preload mounds that we've constructed in advance of the final reservoir. They'll be a slightly shorter than those structures. And the water in the reservoir will appear to be half full, even though it's full. And that's because we need to save room in the event of a storm, and to make sure that we contain waves in the event of a high wind event like a hurricane.
So the height of the water when you've got
The height of the water, since the ground surface varies a little bit within the 10,000 acres, it's about 25 feet deep on the northwest corner towards the Townsend Canal, and about 15 to 20 feet deep on the southeast corner towards State Road 29.
And last question is, are the walls just earth and dam, or is there any steel in there, or sheeting, or is it all dirt?
No, so it's a earth embankment dam, so it's dirt, and it has what we call a cutoff wall. And it's a soil bentonite mixture of clay and soil that ties into a clay layer that underlies the entire reservoir. So it makes it like a big bathtub.
So it's impermeable on the bottom.
Yes.
That clay layer was laid.
Yes, that's why we sited it there, and that's why we chose to tie it in with cutoff walls so that we could minimize seepage out of the reservoir when we're under normal operation, and you know, store the water that we spent so much money putting the water into the reservoir with.
How thick is the wall at the base? I'm assuming it slopes up to the top.
Yeah, it'll be roughly 250 to 300 feet, depending on where you are within the footprint.
Okay, thank you.
You bet.
Our next speaker is Henry Dean.
Henry, don't forget to unmute your microphone.
Mute now. I think I just did unmute. Can you hear me now?
Yes. Hi, Henry.
Hey guys. Hello to everyone in South Florida. Hey, I wanted to shift a minute to water quality as opposed to quantity. And my question is, are there going to be any criteria set before the operation of the reservoir for incoming water with respect to water quality? And also, is there going to be any criteria set for releases into the river? And if so, will that be done in conjunction with the construction? I'll just say as an aside, when we were starting construction on the A1 reservoir in 2006, there was pressure to set adopt a water reservation rule for Everglades water quality issues. So I'm sort of curious as how that's being addressed, if you understand my question.
I think I do, and I'm sure others might chime in. So that's kind of the purpose of the feasibility study. So as the authorized project is commencing, there were no no additional water quality requirements associated with water coming in or going out. The water quality feasibility study will attempt to identify options to improve water coming into the reservoir, improve water that's actually stored inside the reservoir, and then improve water discharging the reservoir. And there may be an option that includes a combination of all three of those technologies, if you will, to improve the water quality in the estuary.
Are there any currently today, are there any federal, state water quality standards that would apply for the operation to go forward? And I don't know, that's why I'm just asking.
Not in the authorized project, there isn't.
But the feasibility study will address what is needed to address water quality issues with respect to the operation of the reservoir, the intake and the outgo. That's a question.
Yes, Yeah, the answer on a broad scale is yes. So hopefully later in this presentation, you'll learn of our short list, if you will, of some of the technologies of water coming both in, staying in the reservoir, and leaving to improve the quality of water that the estuary eventually sees.
Okay.
Right.
It's just-
Yeah, I think we'll get to your question, Henry, in the next segment of the presentation.
okay. I was actually going to ask you if you were going to be answering it later on, but I went ahead and asked because it was on my mind. Sorry.
No,
That's
that's okay.
that's quite all right. A little bit out of my wheelhouse. I'm the plumber, so.
Okay. All right. Thanks, guys.
And that was our last question.
Henry, I think one more just came in.
Oh, yeah, you're right. Here we go. It's Marissa.
Marissa, I can see that you're off mute, but we can't hear you. All right, she put her hand down. It looks like we have another hand.
Pete Quashes.
Yes.
Yes, this is Pete Coltis.
Hey, Pete.
Just curious, are we talking in reservoir treatments, or is there any consideration being given to using the acreage north of the power line?
Right. So all of those options are on the table. So we're looking at both in reservoir before it gets to the reservoir and after it leaves the reservoir.
Okay.
We're looking at a variety of treatment technologies that may or may not include land requirements that might be in the vicinity of the reservoir.
Right. So yeah, just me looking at it as a neighbor.
Sure.
Just you using that surplus land up there seemed like an ideal opportunity, maybe for some low.
Yep. Low hanging fruit.
Yeah.
Yep.
That was
Good question. Thank you.
Okay, I think we should move on to the next section of the presentation. So I'm going to hand the presentation over to Jim Bays to talk about the treatment technologies that we've been researching and looking into for the reservoir project. Jim?
Okay, thank you, Georgia. We'll start off with our new first slide here. Our search for appropriate treatment technologies is focused on three primary water quality parameters. Go to our next slide here. Yeah, thank you. Nitrogen and phosphorus, which are the nutrients that drive algae growth, and suspended solids, which includes algae and organic matter. Nitrogen exists in multiple forms, which vary in their availability to algae, including organic nitrogen, inorganic nitrogen, including ammonia and nitrate. Phosphorus occurs in dissolved and particulate forms, and these have different mechanisms of treatment. So we need to look at all these types of nutrients as in their feasibility of treatment within our systems. Suspended solids represent both a source of nitrogen and phosphorus as in a particulate form, but also a response in the form of algae to elevated nutrients. So all three of these parameters are on our plate here to look at. Next. For this project, because we face significant aerial and operational constraints, we are considering the full spectrum of natural and conventional treatment systems. Natural systems utilize the same physical, chemical, and biological processes for treatment as conventional systems, but where conventional systems build tank-based treatment reactors of concrete, steel, and move water, and add compounds using electricity and chemicals, natural systems are typically land-based systems that rely upon gravity flow and natural plant, soil, and microbes to provide both the media and the habitat for the treatment processes. As a result, fewer staff are required typically for a natural treatment system to operate and less time in the field. Maintenance and monitoring processes are reduced significantly and fewer residuals are produced. And this may mean lower long-term unit operational costs per pound removed. But conventional systems can provide more alternatives where land is limited or expensive, or where greater operational control is needed to achieve certain targets or to respond to changes in flow. Next. In the information collection summary report for this project, which will be available next week, we summarized DEP's library of 33 accepted water treatment technologies, and these include chemical, biological, and physical methods of treatment. We also received suggestions from our working group members, drawing from their knowledge and experience, other treatment professionals in the field, and submittals from vendors and suggestions from the public. So we've received a broad range of inputs here in our choice of technologies. Next. As we reviewed the different technologies, we described them by key attributes. These included whether Florida case studies were available and whether the data were suitable for analysis, the nutrient removal data itself and to what extent it could be used to scale up to treat large flows, the general land area requirements and whether the features were compatible with the reservoir system and its location. And if treatment residuals were produced, how much they would be and how would they be managed. We looked at the amount of energy required to operate the system, schedule for implementing the treatment technology, the operation and maintenance requirements, the general cost for construction, O&M, and the cost benefit, and the regulatory constraints with the provision that the technology can't harm the environment. Next. So I think at this point, I'll turn it over to Chris, and he'll start going through our list, beginning with constructed treatment wetlands.
Thanks, Jim. The first technology, as Jim mentioned, is constructed treatment wetlands. These are large created marshes that are designed to naturally improve water quality. They've been used pretty extensively throughout South Florida, and you might have heard of them in various locations referred to as stormwater treatment areas or filter marshes. They reduce nutrient concentrations by consuming nitrogen and phosphorus for the growth of the wetland plants that reside within these impoundments. And also, those same nutrients are used as energy sources for a variety of microbial processes. There are a number of successful applications of this technology in Florida, and they're widely used across the world. We're fortunate to have very robust operational data sets from large-scale systems within this particular region of South Florida that we can use to guide the design process should these rank highly for this feasibility study. The general removal efficiencies range from about 20 to 40% for total nitrogen, 75 to 90% for total phosphorus, and over 90% for the suspended algal solids that Jim talked about. As these are one of the natural technologies, as Jim mentioned, they require large land areas and therefore have correspondingly large capital costs associated with land acquisition and construction. However, also as Jim mentioned, they typically have lower operations and maintenance costs than some of the conventional technologies that you'll hear Jim describe in a few moments. Most of the annual costs for operating constructed treatment wetlands are associated with supplying electricity to operate the pump stations that are needed to deliver water to or pump water back out of these wetland systems. While most natural systems are not considered as the types of technology that produce residuals, there are residuals that are created within treatment wetlands through the natural decomposition processes of the plants and bacteria and microbes that live in these systems. And what those do is form new sediments in the bottom of the wetland system. That accretion rate is low, typically on the range of 1/2 to 1 centimeter per year of thickness on the bottom, which means that based on the typical approaches that practitioners take to design, that these have a lifespan of somewhere in the range of about 30 to 50 years before any type of residual management would even be considered. This is one of the technologies that the feasibility study team is considering that would be applicable to treat water either before water is pumped into the reservoir or after, as water is pumped out and before it is released back to the Caloosahatchee. Next slide, please. Sand filtration is another passive type technology that relies on the gravity separation of particles such as algae and suspended solids in the water in the C-43 or the Caloosahatchee River. By forcing that water to drain through a bed of sand or similarly sized media. Sand filtration is considered passive or a natural technology because other than pumping, it doesn't require energy or chemical inputs for it to work. There are a number of applications of this technology in Florida, with the largest currently under construction for a phosphate mining facility in Central Florida. Removal efficiencies in a sand filtration system are comparable to the constructed wetlands for nitrogen removal in the range of 20 to 40%. They're a little lower for phosphorus at 25 to 50%, but they're really good for algae removal and suspended solids removal at better than 90% removal. Similar to the constructed treatment wetlands, sand filtration systems would require large land areas and therefore would have correspondingly large capital costs for land acquisition and construction. Again, similar to the constructed treatment wetlands, they have lower O&M costs than most of the conventional technologies we'll describe. And those O&M costs are related to pumping and periodic replacement of the upper sand layer every several years. Again, this is another technology that can be used to treat water on the way into or the way out of the reservoir. Next. This next technology is aeration or air diffusion system, and a difference between this and the previous two is that this is one that would be implemented within the storage reservoir itself. And aeration can be used to reduce algal populations through physical mixing and supplying dissolved oxygen to reduce stratification in the water column and minimize the release of nutrients from anaerobic sediments. There are a handful of applications of aeration in lakes and reservoirs in Florida and a much larger number across the United States. Removal efficiencies range from about 50 to 75% for the nutrients nitrogen and phosphorus. Because this is a technology that would be employed within the reservoir itself, there would be little additional land required to house the blowers and the control systems that would operate the system. One substantial benefit of aeration is that it does not create any residuals that would require eventual removal and disposal from the reservoir. It's anticipated that an aeration system would have a moderate capital and operations and maintenance cost, with most of that O&M cost associated with electrical power to run the blowers. Other O&M requirements would include annual maintenance of the blowers, the compressors, and the diffuser heads themselves in the bottom of the reservoir. And again, this technology, as I mentioned, is applicable within the reservoir itself. Next. The last one that I'll describe is something that's referred to as a hybrid wetlands treatment technology, and this is a nice transition between the three that I presented previously and the technologies that Jim will carry on with, in that it combines the physicochemical processes of coagulation with the natural settling and nutrient uptake processes that occur in treatment wetlands. So in this particular case, a coagulant such as alum can be dosed into the water column and mixed to bond with the nutrient ions, but then form particles that are settled out in the wetland basins. There are several successful applications of this particular technology in Florida, mostly within the northern Lake Okeechobee watershed, where they've been focusing on treatment of water in tributaries to the lake that are highly influenced by agricultural operations. These have been very well-studied systems and have robust operational data from which we can go forward to the feasibility study. Removal efficiencies for the hybrid wetlands technology range from about 50 to 60% for total nitrogen, 80 to 90% for phosphorus, and about 90% or more for suspended solids. In part because they're enhanced or intensified through the use of chemicals, They would require a slightly reduced land area when compared to a more conventional constructed treatment wetland system, and therefore would have reduced capital costs associated with land. The requirement for chemical addition, however, increases their O&M costs relative to treatment wetlands and sand filtration. They do generate residuals, a solids, a flocculent material that would require periodic removal and disposal from the settling basins. This is another technology that could be used to treat water either on the way into or the way out of the reservoir. Jim?
Okay. Well, the other technologies that, like Chris mentioned, speaking to coagulation, involve a more dedicated facility where an offline or an online treatment system is established. In this case here, we're using the addition of a metal salt or a coagulant to change the particle charge of particles within the water column itself and encourage the growth of particle size and their sedimentation rates. And this is a common approach for treatment of drinking water supplies. As well as a reduction of phosphorus and nitrogen from advanced wastewater treatment systems. In our case here, these would be either as an offline system treating water coming in or within the reservoir itself. The multiple Florida applications shown here is one large-scale facility in operation in Lake County, Florida, the nutrient reduction facility. These are well-studied systems. There's over 30 years now of treatment using alum injection in Florida, lakes and reservoirs and stormwater systems. And these have been built for fairly large flows, like the one shown here. The nitrogen removal is significant. Typically, we see 50 to 70%. For phosphorus, it's even better, 50 to 90%. And solids reduction is also equally high, over 90%. These chemical processes react quickly, so we don't need much land area for the treatment process, but there is land required to settle out the solids and collect and store them until solids processing can take place. Therefore, the overall capital cost may be relatively low, but there's a significant O&M effort, operational effort to collect those sediments, the floc or the alum residuals within each of these systems, and dry that and process that and store it and dispose of it. The overall requirements for power are involved primarily with the pumps to move the water, the mixers and dosing mechanisms to apply the alum, and to make sure that it's properly coagulating. And then the actual process of removing solids can be done typically with a hydraulic dredge in a situation like this. So there's power to feed all those systems. But this could be configured to be both a pre and post storage treatment system. It could be, alum could be added as an inflow to the reservoir and mixed in the dynamic process of the water flowing in and settling out within the reservoir itself. So that's one concept there. Let's go to the next slide. So in the reservoir itself, there's, in addition to aeration, there's an opportunity to control the algae directly. One technology that's out there is an innovative approach to treat the water during storage using the MPC buoy system. This is the use of ultrasound emitted at wavelengths in the water that disrupt algal cell flotation mechanisms and interfere with the natural buoyancy of algae cells and prevents them from staying in the upper well-lit portion of the water column. This affects their growth and keeps algae from growing to bloom proportions for the project. The vendor has embedded a floating buoy here in this case, and it's solar powered, and the ultrasonic emitter is suspended from the buoy. There's a limited number of data available on this, of studies on this technology in the United States. There are currently pilot studies being planned and being conducted in Florida, just beginning. But there's a significant body of information about work using this approach in Europe. When the findings has been that the system can reduce algae significantly by up to 90%. Another feature of this approach is that, once again, we're not really building a separate system, that we're actually confining the treatment technology to the reservoir itself as they float on the water surface. And it would not produce residuals like we're seeing for the other technologies. It's relatively low capital cost to install these, but the operational effort would be moderate in the sense that they have to maintain the transducers and the buoys over the course of a year. This would essentially represent a treatment during storage configuration. Okay, next. Electrocoagulation is another form of coagulant addition for nutrient control. The working principle is basically the same, where the charge of a particle is modified by addition of a metal ion to the solution, which allows particles to grow and settle. In this case, however, instead of a metal salt like alum, an electrical charge is directly added to the water through a metal electrode, and the metal ions are released from the metal plates. The system typically includes a sedimentation tank for collecting the coagulated solids. There are a few Florida case studies, mostly consisting of pilot and bench scale tests, and there are limited performance data, but the technology has been in wide use across the world for decades for treatment of industrial wastewaters. Available pertinent data indicate removals of 60 to 90% nitrogen, more than 90% phosphorus, and 90% algae can be expected. Of all the offline treatment technologies we're discussing, this system will likely require the least land area, given the rapid treatment time, which is on the order of minutes, and the relatively smaller amount of solids produced, approximately 83% less than what we'd see for alum treatment. The capital cost is relatively high, given the highly engineered flow, treatment, and solids handling facilities needed. And O&M costs will be relatively high as well, given the higher electricity requirement, electrode replacement, pumps, dosing mechanisms, and air injection. The amount of residuals produced is less than what can be expected from a use of chemical coagulants, and given that the only solid added is just a metal ion from the electrodes, this technology would be considered for pre and post storage. Next. A more passive treatment technology is the use of a phosphorus sorption media, where nutrients are bound chemically to surfaces of substrates such as sand, clay, or organic materials selected for this property. In Florida, an increasingly common application is the use of Golden Gold, an engineered sorption media developed at UCF for stormwater and surface water applications. This material comes in a range of formulations, which can include sands, clays, iron particles, and tire crumbs, all of which exhibit phosphorus sorption potential. There are a number of applications in Florida, and a number of publications and performance studies have been completed. Nitrogen removal is typically good, on the order of 75 to 95%, and phosphorus is as well, 50 to 90% phosphorus. Because of the high flow rates that the media can take, land area requirements are moderate, and the capital costs are also in that moderate range. Typically, these systems are built in vaults or shallow detention basins, but they may also be built into the berm of a basin or provide final polishing to water infiltrating from the basin. O&M costs are relatively high given the cost of replacing and disposing of spent media, although it's on a relatively long interval, and it's estimated to be on the order of, say, 15 years. This technology could be applicable to a pre and a post-storage application. All right. The Nutrigon biologically activated media, or BAM, product is a phosphorus sorption media combined with an organic carbon media designed to remove phosphorus and nitrogen when water is passed through it. Typically, it is designed as a flow-through filtration vault, but can be designed also as a large filtration basin. There are limited applications in Florida at this time, and available bench scale studies indicate that up to 90% removal of nitrogen and phosphorus can be expected, but available performance data show a more varied outcome and performance. Because it is a filtration system with sorption media, this technology would require a moderate land area. The capital cost would be high because of the engineered media, and O&M cost would be high because of the need to replace the media frequently. The volume of spent media needing to be disposed of would be significant, but power costs would be limited to just simply what it takes to move the water in and out of the system. This approach would be applicable to pre-storage and post-storage operational phases. And finally, there's the Aqualutions approach, This is a technology that's a combination of chemical addition to coagulate algal solids, followed by dissolved air flotation to separate the coagulated solids. The outgoing product is very clear water with low nutrients. Several pilot studies have been conducted in Florida, the most notable being a 5-year study treating water from Lake Jessup in north central Florida. Available data from that project and tests by the district have provided a reliable performance basis. Nutrient reductions of 65% total nitrogen, 90% phosphorus, and 80% algae reductions were achieved in that study. The treatment system operates within a relatively compact footprint, so the low land area requirement is not great. The capital and O&M costs are high, relatively high, given the chemical and mechanical components. As with other solid separation techniques, a large volume of solids is produced that must be dried and disposed of. In lieu of landfilling, because the residuals do contain nutrients, the vendor promotes their use for fertilizer pellets, but they can also be burned as well. Another factor to consider is the power cost to operate the mechanical components, including pumps, air compressors, and solids management systems. This technology would potentially be suitable for a pre and post storage. So that's the overview of our relatively short list here of technologies. Are there any questions about any of this material that we presented?
Thanks, Jim and Chris, for going through those technologies and giving us the pros and cons for each of them. Looks like we have a few questions coming in. Henry, would you?
Our first speaker will be Thomas Van Lent.
Yes, I had a couple of questions. I noticed you talked about, well, first of all, I'd like to just say I'm really extremely pleased to see this whole process, that this is a very important issue, and I'm gratified to see the Water Management District and the DEP taking the lead to address water quality in the Caloosahatchee with a project like this. So it's really congratulations and thank you. My next question was, I noticed that you keep discussing everything in terms of percent removal and not in terms of, say, a TMDL or numeric nutrient criteria. So my question kind of is, are you going to more or less determine the removal from the technology, or are you going to select a technology based upon a removal goal or some sort of cost basis, or what are the criteria for selecting one of these technologies?
Right.
Do you want me to take that one, Jim?
Do you want to start it? I've got some thoughts on that, but you're welcome to start that.
Well, what we're going to do with the study is we're going to evaluate these technologies on a cost-benefit basis. We're going to look at their construction and operational costs and compare that to the removal rates. We are not expected, and we'll touch on this a little bit later in our frequently asked questions session, that we are not targeting a TMDL. We hope that we expect that the technology will add to the TMDL, to the goal, but we are not looking at a specific target for the purpose of this study. Jim, did you want to add anything to that, or should we go to the next question?
Oh, well, Thomas, you had a second part to your question. Why don't you ask that, and then we'll see if we need to expand that answer better.
No, I think that was my key understanding, okay. Is what are the criteria for selecting a technology? Because a lot of these are pretty experimental, and so you're going to have some latitude in the cost. If it's a cost-benefit ratio for removal efficiency, I think that's important to understand at the outset to evaluate the project.
Right, and just I'll expand just briefly, George, if it's okay. We intend to develop some planning scenarios in our next phase of this project. The next, now that we've got our short list, we'll develop assumptions of flow and ranges of concentrations for nitrogen and phosphorus to treat. And we'll be working with the vendors or the literature available to estimate treatment performance under those flow conditions for those nutrient concentrations. And we'll then calculate a cost benefit for that removal efficiency. So to Thomas, your question, the percent removals is really just a marker for us right now. It's not really the final basis. We'll look at the treatment performance in a more detailed way in the next section, next phase here.
Thanks, Jim. Do you want to go to our next question, Henry?
Our next speaker is Robert Himshoot.
Yes, my question regards the disposal of the material.
Yes, sir. Is it more of a question of, how to do it, or it's certainly a factor, if I could say, it's certainly a factor in our review of these technologies. There will be, as we've described here, conversion of all these nutrients and some of the algal solids into a solids that has to be disposed of. That sometimes that can be reused as a soil amendment, and sometimes it's simply a matter of landfilling or storage or burning it to dispose of it. That there's no one answer yet on that. Every technology has its own mix of solutions to that problem, but it is a factor that we'll look at in terms of the land area required for storage and the power requirements for processing and so forth. Does that respond to the question?
Partially, but I was wondering, as you discussed the nutrient loading, whether it could be used for compost or whether it would be go to a class 1 landfill or a C and D disposal site. Those are the basic options that I was hoping you'd address.
Fair enough. And I think that we'll definitely get to that level of detail in our next phase here as we look at each one. Because to answer that question properly, we'll have to have some assessment of the cost to manage the residual, and that cost will vary depending on the storage or disposal the alternatives.
Thank you.
You're welcome.
Our next speaker is Ernie Cox.
All right, had to click the button to unmute myself. Yeah, thanks everybody. Just wanted to get a sense of how long you think it'll take you guys to go from kind of the qualitative criteria that you just went through to having some pretty good numbers to do comparisons of technologies and cost. What do you think that timetable might be?
Georgia, I'd look to you to kind of step back to the schedule there. Ernie, we're going to get into this phase really fast and heavy here in the next few weeks here, frankly. But Georgia has the exact dates on when you can expect the next output of this.
Yep, I'll be talking through our next milestones in a few more slides from now, and we'll have a preliminary assessment in June, and our final report is expected in October of this year.
Fantastic, thank you.
Our next speaker is Matthew Schwartz.
Can you hear me?
Yeah.
Yeah, okay, I've got a microphone on now. 2 questions. So with regard to the stormwater treatment area / filter marsh option, have you guys worked out how many acres would be required if that was elected? Is there any preliminary numbers on that?
This is Chris. I'll go ahead and take a start at that answer. As Jim mentioned, we'll be going into this next phase of the project here in the next few weeks, where we'll be developing kind of those standardized inflow data sets on flows and water quality that will be used to further flesh out each of these alternatives and be able to provide a fair basis of comparison between them. It'll be during this next effort that we would develop sizes for what a stormwater treatment area footprint might be based on those assumptions of inflow or outflow water quality and inflow and outflow flow rates. So not yet, but very soon.
Okay, I've got one other question, a little more difficult. And it's really simple, but why are we doing this now instead of before construction began? Because clearly some of the options presented would be much easier done as the construction takes place, especially that compound that would be part of the berm itself to absorb nutrients. And that's an obvious question I think a lot of people have, is that why is this being done after construction began as opposed to a part of the pre-construction phase of this?
Yeah, I think that question is, I don't want to put you on the spot, Matt Morrison, but I feel like you would probably have the best answer for that
Sorry, Matt.
question.
That's quite all right. Can everybody hear me? I assume I'm unmuted.
Yes.
Well, I can tell you that in the CERT project, this particular reservoir did not evaluate stormwater treatment like the reservoir over on the C-44 canal over on the East Coast. And it became apparent over a couple of years, including the last 4, that algal blooms are a problem in the St. Lucie River and estuary. With that said, we had the project authorized by Congress. We've had the funding available to implement the reservoir. We've got our contractors out there building, and all of that was occurring while we started to recognize that we needed to start to address some of the water quality concerns in the Caloosahatchee River. So it was really just a matter of timing. The federal project itself that this C-43 reservoir did not contemplate a water quality improvement component. And we're moving forward in the Comprehensive Everglades Restoration Program and building that reservoir facility to improve the quantity, timing, and distribution of flows to the estuary. And when I say, quantity, timing, and distribution, it doesn't include the quality piece. So based on information that we've received over the last several years on water quality and the considerations that need to be made, we are looking at implementing this now, recognizing its importance outside of the federal program. So hopefully that answers your question, Matthew.
More or less. Thank you.
Okay, and our last speaker looks like it's Ray Ann Wessel.
Rayanne, we can't hear you. I know your microphone is off mute, but I don't think it's working for some reason. Henry, do you want to go to Marissa?
I mean, Georgia, also, this is Jim. I mean, maybe Rayanne could type her question in if she can. I think we can see chat type.
We'll have more opportunities as well later. So.
Sure enough. Okay.
Marissa? I'm not sure why we're not hearing the participants.
Can you hear me now?
Yes.
Ooh, can you hear me this time?
Yes, we can hear you.
All right, figured it out. Thank you, everyone. This is Marissa Carozza with the Conservancy of Southwest Florida. First of all, I would also like to echo the thanks to the district and DEP for moving forward on this really critical aspect related to the C-43 reservoir. Having water quality treatment associated with the reservoir has been a long time priority for the West Coast stakeholders, so thank you. I had kind of a two-part question. One, in evaluating the cost benefit of these various treatment options, can you first speak to the scalability of using kind of a treatment train approach to reach max treatment capacity that's cost feasible? How are you approaching it from that standpoint?
Do you want me to start that answer, Georgia?
Yeah.
Okay,
Yeah, go ahead.
fair enough. All right. Okay, so Marissa, I think right now our procedure is to look at each technology as it sort of stands alone. That is, could an alum system be used for a pre or post system by itself? That's primarily just to try to simplify some of the costs, well, let's say expedite some of the cost comparisons and make it a little more directly comparable between technologies. But I think I take from your question that these technologies could be combined in some way to maximize performance. We're looking at getting to a short list of 3 by the time we're done here. It's not inconceivable that we might think of a reservoir treatment as well as a inline or offline pre-storage treatment system, or some combination of those as a final either potential configuration. So I would say that we're anticipating something like that, where we look at a combination of technologies, but for the most part, we're really focusing on each technology as it stands, trying to standardize that comparison. But I do take your point; these things could be configured in some combination. But our approach right now is to take them kind of uniquely here and then see where we stand at that stage. Does that respond to your question?
Yes. So as a follow-up, the 3 alternatives that you would identify at the end of the feasibility study, those would be 3 separate treatment technologies, or not necessarily 3 different alternatives utilizing multiple treatment technologies?
Right, exactly. We'll have 3 that we think are that will ultimately come out to have the lowest probably cost for the unit benefit, whether it's pounds per phosphorus removed or nitrogen or solids. It'll be based on that kind of a metric. But there are other things we want to consider. For example, are there habitats created by the system, as you might expect for, say, an STA type system? There's some other variables that we'll look into going forward here, but we're really going to ultimately rely upon a cost comparison basis. And so conceptually, out of that, 3 alternative technologies, the district could move forward with one of them and still meet the objectives of the water quality treatment. It might remain to be seen down the road if there's a need to look at more of these or a combination of them. But I think right now we're thinking at the end of the day, well, out of these 3, one technology would be able to handle the assignment. Does that also respond? Okay.
Yes, thank you. And I do want to respond briefly to your point about habitat. I think that would be a really good variable to keep in consideration as you evaluate the technologies. That the habitat benefits from some of these would be very important to consider. Thank you.
Yeah, some are better than others at that. That's right.
Thank you.
Thanks. Jim, I was able to see Rayanne did type in a question, so I'm going to read it for you for a quick answer. It's, have you determined the fate of alum in the environment in the hybrid wetland system?
There has been, we're relying upon the literature that's been produced by the districts and by the proponents of the technology. There has been work done on the fate of aluminum in these systems that ultimately they're lost as a flock or just sedimentation into the system itself, and that flock is removed periodically. So the findings so far have been no toxicity concerns, and this generally is consistent with what we see for the application regionally and nationally. And in 2018, the EPA did issue a a new aluminum water quality toxicity criterion. And we'll be looking at that in this regard here too, to confirm that there wouldn't be any associated toxicity with any of these dosing systems that we're talking about.
Okay, great.
I hope that's responsive. Yeah.
Thank you. Okay, I think we'll move on to next steps. Thanks, Sean, Jim, and Chris for providing the details about the reservoir and the technologies that we're focusing in on for our study. I'd like to highlight our upcoming milestones for the project. We look forward to all of you participating again on our July 16th meeting at 2 p.m. As I mentioned earlier, we plan to have the preliminary draft feasibility study in June, and the final will be completed in October of 2020, and we will present the final results in November of this year. But because this is our first evening meeting, we thought it would be helpful to review some frequently asked questions before we get to our Menti interactive section of the meeting. So generally these questions were asked at previous meetings or sent to our project email address. So I'm just going to read through these couple of slides to give you an overview of what we've been asked in the past. So the first question is how much land is available? And available land specific to this project has not been identified as part of this phase of the study. It will be incorporated as one of our evaluation criteria. Is there a goal to be achieved for the water quality treatment project? And the focus of this study is to ensure improved water quality leaving the reservoir. The C-43 operational permit will set water quality requirements for water discharged from the reservoir. Are all treatments environmentally friendly, and the technologies included in the study cannot cause harm to the environment? How is nitrogen and phosphorus sequestered in the C-43 reservoir project test cells? So during the preliminary evaluation of the project site for the reservoir, they built test cells, and phosphorus and nitrogen data was collected during that time, and both nitrogen and phosphorus saw a decrease over time during storage in those test cells. I think Matt already kind of answered this question about why wasn't a stormwater treatment area always part of the plan, so I will leave that one for now. When is this project due for completion? And the substantial completion of the reservoir is scheduled for 2023, and the study is to be completed in November of 2020. So the next question is about the TMDLs, and the total nitrogen TMDL load reduction was sent for the entire Caloosahatchee River and estuary watershed. Any reduction in nitrogen from the water stored in the reservoir or associated water quality feature will be included as part of the overall reduction for the watershed. How large an STA is needed to treat the volume of water released from the reservoir? Approximately 5,000 acres of land is required for that volume of water. And will the reservoir be lined? And the reservoir is not lined. The bottom of the reservoir will remain native soils, and Sean kind of discussed that earlier. So I wanted to remind you that all of our study information can be found on the Water Management District's website. Please go to sfwmd.gov for the working group's webpage. And we also have the project-specific email address where you can send additional comments and questions to the project team. The email address will be active throughout the study period, and it is the C-43 waterquality@sfwmd.gov. For the next portion of our presentation, I mentioned earlier, we want to go to this Menti interactive technology. If you go to either menti.com in a separate web browser or on your smartphone, you can enter the code 17566, and you don't need to put spaces in between, or you can, and hit enter or hit submit, and you will be hopefully seeing something similar to the Menti screen. And I'm going to pull that up now, give you time to get logged in to Menti. I'm going to give you a few seconds. Everybody can get into the menti.com. If you're streaming this through YouTube, the public input portion through Menti will be delayed, so you won't be able to participate directly. However, please feel free to email any questions or comments you may have to the email address c43waterquality@sfwmd.gov. And we want to thank the Coastal and Heartland National Estuary Partnership for allowing us to use their Menti program. It's a unique interactive tool that we hope that you will enjoy to provide your feedback. So let's warm up with a few questions for you guys. This is when we get to ask you questions. So hopefully you can all see on your Menti screen and in Zoom, the question on the screen is this the first public meeting for the C-43 Reservoir Water Quality Feasibility Study that you have attended? And I'm seeing all the answers come in. You won't be able to see the answers on your smartphone, but if you are still in the Zoom meeting, you should be able to see the answers come in on the screen. So far we have 29 responses. We'll give it a few more minutes to get some more answers to come in. All right, we're up to 31. All right. All right, well, it's good to see we have 20 or so new attendees to our study meetings. All right, I'm going to move on to the next question. It's another warm-up question. List one or two words that immediately come to mind when you think of the C-43 reservoir. And you can type that into your screen. I think they give you an option to type in a couple of times. And as multiple words are used, are typed in, or the word is typed in multiple times, it gets bigger on the screen. We have 29 responses so far. I'll give it a few more seconds to get a couple more responses. As a heads up, at the end of the Menti session, you'll be able to enter your email address and receive a PDF copy of the answers for all of our questions today. All right, 37 responses. That's great. Thank you all for giving us those answers. So the next slide, the next question is, what type of technology would you like to know more about? Of the technologies that were presented today, the biological, chemical, and physical treatment options, which ones would you like to know more about? All right, biological is winning the race right now, with physical in second and chemical in third. I'll give a few more seconds for people to type in their selection. Okay. Biological wins on that slide. So a lot of you have seen technologies like these used successfully in Florida. So we'd like to know the name, location, and technology type of projects you've seen in Florida. No other technologies? We have STAs. I know the working group has seen a lot of technologies used. There they go. Now we're getting some answers. Great. Hopefully y'all can see the great responses that are scrolling up on the screen. And again, we'll be capturing all of these answers. And we will have them available for review on our project website in the coming days. All right. So I think for the matter of time's sake, we'll move on to the next slide. People have a couple more answers they want to get in. Okay. So during the presentation, we talked about evaluation criteria for the technologies. So for this slide, we'd like you to add any additional evaluation criteria that should be considered in our study as we move forward and whittle down the technologies down to 3. So on your Menti screen, you should see a list of things that we are already considering, which are, cost, land requirements, things of that nature. All right, these are great answers. I'll give you a few more seconds to type in any responses. Okay. So this slide, we'd like to know what information you would like to hear about most at the next public meeting regarding the final 3 alternatives to be selected. And you can scroll on your Menti screen, indicating which is least interest and which is most interest to you. All right, looks like cost benefit analysis is in the lead. Okay, I'll give you a few more seconds if you want to put your response, and then we'll move on to the next slide, which I believe is more questions and answers. All right. So rather than deal with raising your hands and unmuting, we're going to ask you to type in any questions that you have related to the reservoir storage project. This is related to the C-43 reservoir, not necessarily the study or the technologies, but the reservoir project itself. And Sean Waldeck will hopefully be able to answer your questions. So we'll take any questions now. Any additional questions?
So will an operational plan allow recycling of water within the reservoir? Right now, the reservoir allows for flows in through the major pump station, and it can flow from one cell to the other through some control structures. But within the reservoir, the only alternative that we mentioned in our study was the air bubbles to help move the water through the system. So many questions. So are there any ways that storage benefits can be increased by multiple fillings? So part of the operational plan is to essentially fill the reservoir once per wet season on average, and then discharge once per dry season on average. Essentially, we'll be looking at conditions in the reservoir at any given time of the year and make some estimates or evaluations as to whether or not we we can take more water in or deliver more water out, depending on climate forecasts and the like. Could a filter marsh be constructed within part of the reservoir footprint? Unfortunately, no. We have very specific instructions that we have to build the reservoir as authorized by Congress. That's how it's funded. That's how we're going to get our cost share. So all filter marshes will have to be outside of the reservoir footprint.
How about one more question, Sean, and then we'll move on to the next slide.
Sure. Well, we empty the reservoir once a year on average, and then how does the volume, the C-43 reservoir volume, need to be treated to compare to the treatment options presented? So I think as we mentioned, the normal low water discharges will be in the 457 CFS range, and an STA, for example, or other treatment plant type facility would have to be sized to accommodate that kind of flow in order to meet the demands of the river when the river and the estuary call for it.
All right, thank you. We're gonna, all these questions will be captured, and we will do our best to respond to them through the website, through the project website after the presentation. So the next question is, please type in any questions you have related to the technologies that are being evaluated for the studies. So we have 10, and I believe there are some questions about these technologies. Any additional questions for Jim or Chris to address? More questions? Oh, here we go. Oh, can you list the 10 one more time? So we have stormwater treatment areas, we have sand treatment systems, we have aeration, we have hybrid wetland treatments, we have coagulation treatments, we have BAM, Golden Gold, aqualutions. We have the buoy system that treats the algae stored in the reservoir. Jim, did I miss any? I feel like I missed one.
This is Marcy, electrocoagulation.
Thanks, Marcy.
So Georgia, do you want me to start
yes.
responding to these? So the middle question here, is there more detail on the technologies on the website? The answer is yes. Our literature summary does go into description of each technology, characterization of some of the case studies and performance data available from those. We have descriptions of the management needs, and a lot of this is based upon what's generally available in the literature, or specific information provided by the vendors. But when you can learn a lot more about what we're talking about on the literature summary, for sure.
And that'll be available on April 3rd on the project website. And we also have a huge literature library that is available on the website right now with that has numerous studies and technologies related to water quality improvement.
You go to this one here. What happens if the chosen technology stops doing what it says it will? I think that's actually a really good question, because we want to only present and select a short list of technologies that are very robust and that have been proven or are based upon sound principles. So I think the issue here is that when we get to the final list, it will be some presumption then that it will be able to perform under long-term conditions and meet the rigorous requirements of this scale of a project. So if it to the potentially at that stage unlikely scenario where it wouldn't be performing what it says it will, I think that would be a case where the planning for the project itself, the specific project, would have built in their remedies or other approaches that can be used if there was some shortcoming in the technology. But like I said, I think our plan here is to make sure that we get down to a short list that everybody is confident in.
How about the one about floating treatment wetlands in the
Yes.
reservoir?
Okay. Right. We've floating treatment wetlands was on the original list and still is a viable and active technology and actively applied technology in the state. Our considerations here were based largely upon several constraints. We didn't move floating treatment wetlands further into the final list here. Primarily because of the nature of the reservoir environment. We're looking at very large surface areas, very large fetch development, that is, wind orientation and movement of water and response across the surface. And this in the typical fairly robust anchoring requirements for flooding wetlands under these conditions. Pretty much put this on a category of difficult to implement or uncertain, greater uncertainty of implementation. So they got put off to the side here. Having said that, there's certainly opportunities in the future to look at flooding wetlands both as part of the wetland system or as a part of a wetland system or as part of something like, say, the hybrid wetlands treatment technology where they do in fact promote the use of floating aquatic plants to provide some polishing. Okay.
I'll tackle this one about as nutrients are removed, will there be a discussion of how the chosen treatment might perform? For example, at 100 parts per billion TP, you might remove 70%, but will that removal be expected at 20 parts per billion? And that's where we're going in this next phase of the project, where we'll be developing the inflow data sets that will describe assumed water quality conditions in flows that will be pumped to the reservoir, within the reservoir, and discharged from the reservoir. And that's the time at which we would look at how the kind of screening level percent removals relate to actual performance at those ranges of concentration. There may well be some of these technologies that have made the short list that will drop out because the inflow concentrations that will be typical of the reservoir system are lower than the literature-based values and the previous studies that have been done, what the water quality conditions were during those particular studies. So that is something that will be looked at. We don't take the percent values as gospel by any means, and we'll certainly be looking at treatment effectiveness as it relates to inflow concentration and concentration reduction goals.
Mm-hmm.
Okay. As I mentioned, we'll pull all these questions and provide detailed responses on our website in the coming days. I just wanted to give you one last opportunity to add any additional questions for the study team or for members of our working group that are also on the phone and our water management district team. And folks from the water management district and the working group, if you see a question you'd like to tackle, just remember to unmute your phone and chime in. I will answer the first question, and the slides from the presentation will be available online, again, along with the mentee questions and responses. All right, we have a couple questions on the screen. Other than that one, thank you for the compliments. So the study is not part of the CERT plan. This is a separate study being pursued by South Florida Water Management District.
Georgia, I'll take the one on, is there possible use of ASR for nutrient reduction? In this particular part of our 16 county jurisdiction, we drilled some pilot wells in the CERT program for the use of ASR to be co-located and work with the C-43 West Basin storage reservoir. And based on the technical data from our investigations, ASR technology is not a good application in this particular location.
Thanks, Matt.
Georgia, this is Kim Fikowski. When will it be published online? As Georgia has said earlier, everything is on the website, the working group website that was posted earlier. You go on to the Water Management District and you look at the priority projects, you'll see the C-43 water quality feasibility study, and that'll link you right to it. And everything that has been done for the study will be online. So April 3rd, that information technology report will be online in addition to these questions and this presentation.
And as a reminder, the next public meeting is July 16th at 2 p.m. Are you sure that's what I said?
Yes.
And, we look forward to everyone's participation there. We have one last question for the participants. We'd really like your feedback about the format of this meeting. If you thought it was productive and meaningful, do you think it was a valuable way to collect input? And if overall you felt that the meeting was a success. So please provide your responses through your Menti program. All right, we'll give you a little bit more time to get some feedback. And in closing, I just want to say that we really appreciate your participation. Again, thank you to CHNEP for letting us use the Menti program. Thanks to the working group and the Water Management District for your input and support. And we will be posting the Menti results on the project website, along with the PowerPoint presentation. And with that, I think I will close the meeting unless anybody else had any additional comments at this time.
Georgia, this is Kim Fikowski. I wanted to let everybody know that I think you had mentioned it earlier, that at the end of the Menti, you actually can put your email address in and have all of the responses sent to your email.
Great, thanks. Thanks for that reminder.
Georgia, this is Drew. I just wanted to thank everyone for participating. The feedback was great. And I just really want to thank the team for pulling this off under the circumstances. I think given that, it was very successful. So thank you, team.
Great. Well, with that, I hope everyone has a safe and good rest of your evening. Thank you so much. Bye-bye.